Today we're going to talk about infinite geometric series. So we've already talked about how you can find sums of finite geometric series. Now what we're going to do is we're going to find sums of infinite geometric series. And also we're going to write repeating decimals as fractions. So some of the new vocabulary is that I'll be defining is infinite geometric series. We'll learn what's meant by a convergent series, a divergent series, and infinity. So the first thing I want to do though is I'm going to be showing you a little video that I had my calculus students kind of help us out.
All right, there's 8 meters approximately from the window to the door. So, Gage, please walk halfway to the door.
Go, Gage.
So how far has Gage walked?
4 meters.
Okay, 4 meters. Now go ahead and walk halfway to the door. Okay? So how far did he go that time? 2 meters. So go halfway to the door. So how far did he walk that time?
1 meter.
Go halfway to the door.
Half a meter.
Okay, now, hold on. If Gage were to continue doing this, theoretically, when would he reach the door? Never. Because he would always just be going half the distance. But how far is it from the window to the door?
Okay, so what Gage just showed you is actually kind of the idea of an infinite geometric series. So I first had him walk, first of all, if this distance here was 8 meters from the window to the door, and I had him walk halfway. So that means he walked a total of 4 meters. And then he walked halfway, which would be 2 meters. And then halfway, which would be 1. Halfway, which would be a half. Halfway, and we could keep chopping that in half. So if I wanted to come up with a sum for the total distance from the window to the door, it would be 4 plus 2 plus 1 plus a half plus, next would be a fourth, plus an eighth, plus a 16th, plus dot, 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 and it never stops. So it can keep getting smaller and smaller and smaller. However, we know that if we were to add all those numbers up, it has to be 8. And so this is what it is meant by an infinite geometric series. Now sometimes an infinite geometric series will have a sum and sometimes it doesn't. Now let's recall how we know it's geometric. If I were to take if we think of this as a sequence, we would have 4 and comma and then 2, 1, 1/2. So if I were to take successive terms, so if I take 2 over 4, we get a half. 1 over 2 is obviously a half. If you were to take a fourth over a half, remember when you divide by a fraction, it's the same as multiplying by the reciprocal, so we get a half. So we have a common ratio is 1/2, so we know it's geometric. So that's why we know this is a geometric series. And because we're adding up the terms of a geometric sequence, and because it goes on indefinitely, it never ends, that's when it's called an infinite geometric series. So I could do the same idea with this, starting with a square. If I were to break it in half and then have this side as a half, but I could chop this remaining piece in half again. So now this piece is a fourth, and then I can chop this in half again. So this would be an eighth of the original square. And if I were to break it in half again, this piece is 1/16 of the original square. And I could keep going. And if I were to keep going, I'll do one more. I get 1 out of 64. Now, physically, at some point, I won't be able to make them small enough, but if I were to take this and add 1/2 plus 1/4 plus 1/8 plus 1/16 plus dot, 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 because it's going to keep going. This is an infinite geometric series. However, how much of the square is going to be represented when I add up all those pieces? I get a sum of 1. Now in this case, if I were to take 1/4 divided by a half, so a fourth times the reciprocal, once again, I have r is a half, and you could see that if you took some other terms as well. So again, it is geometric, and this is what's meant by an infinite geometric series. So the situation that you'd want to look at to tell if it's going to approach a value or if it's not, it depends on what your common ratio is. So if your common ratio is less than 1, both of the examples I did, r was 1/2. So that would be an example. So if it's less than 1, or the absolute value of r is less than 1, because remember sometimes r can be negative as well, then you're going to have, you will have a finite sum. And we call that a convergent series. So it converges to a value. And if you were to graph this, the term versus the sum, you can kind of see it levels off to some value. Whereas if the absolute value of r is greater than or equal to 1, then what's going to happen is you're going to have, for each successive terms, the sum is just going to get huge. And so then we call that a divergent series. So it doesn't, you don't have a sum in that case. So here's an example. Determine whether the infinite geometric series is convergent or divergent. So it really is all about the value of r. So we have to see what our value of r is. So if you take the 243 over 729 and you evaluate that, well, actually right away, even before I go on, I am going to make sure it's geometric. However, I can tell that if it is, that it's going to be convergent because I can see right away this is less than 1. So in this case, since, oops, calculator disappeared here. Get that back up there. So in this case, we can see that r, when I divided those out, I get r equals 1/3. So so since r equals 1/3, and that's less than 1, so then this series we would say is convergent. And if you were asked to find the sum, now we could do that. We're going to have a formula for that in just a minute. Okay. For this next one, determine whether this one is convergent or divergent. So we're going to take 5 over 2 to calculate the value of r. Well, I can see right away that's 2.5. So since this is bigger than 1, then this series is divergent, which means the sum does not exist. So go ahead and calculate this, decide whether this is convergent or divergent, and make your choice. And then you have another problem to do as well. I'm not going to provide the answers on here, so please pause this and go over those 2 questions with your group, and we'll talk about that later. Okay, as we go on, for this, we have a formula now to actually calculate the sum if it is a convergent series. So the sum S of an infinite geometric series with the absolute value of r is less than 1 is given by, and so we have this formula. Now this should be put on your note card. Notice that there's no subscript. It's not S sub n because it's not a partial sum. It's actually the sum of the whole series. So all you need to know is the initial term and the value of r. If the absolute value of r is greater than or equal to 1, then we would say the series has no sum, or the sum does not exist. So for this problem, part A, find the sum of this particular series if it exists. So the first thing we have to determine is, does it exist? So we're going to calculate r. 4 divided by -4/3. So I'm going to take that times the reciprocal. These cancel. I get -3, and because the absolute value of r is greater than or equal to 1, so then the sum does not exist. On the next one, I'm going to take -3/2 divided by 3. So I'll change that to -3/2 times 1/3. 3's cancel, I get -1/2. Since the absolute value of -1/2 is less than 1, then the sum exists, so now I have to find it. So I'm going to use my formula. S equals a sub 1 over 1 minus r. Whoops. So I get 3 is the first term over 1 minus -1/2. Change that to add in the opposite. So I have 3 over 1 plus 1/2 is 3/2. So I'm going to change this to 3 times the reciprocal. The 3's cancel, because remember this is 3 over 1. So my answer is 2. That would be my sum. Okay, you go ahead and try this one. Find the sum if it exists. I think there's a part D not showing up on mine, but you have this on your paper. So go ahead and you're going to pause the video. You're going to answer this and compare this answer with your group. And then we're going to go ahead and do this problem and compare that answer with your group. So go ahead and pause the video. And then when you're ready to go on, hit play. Okay, on this next one, to evaluate, now we have it in sigma notation. So I want to review with you what that means. I know most of you are going to, well, actually, you wouldn't be able to do this in your calculator because we're going from 1 to infinity. So when you do this, we're going to have to figure out what the pieces are in here. Remember that this portion right here is just my expression for a sub n. And remember that for geometric, a sub n is equal to a sub 1 times r to the n minus 1 power. Now they used a k here instead, but this is my expression for a sub n. So in this problem, a sub 1 is 5 and r is 1/2. And remember, that's all I need to know to find the sum. So I'm going to take my formula, a sub 1 over 1 minus r, and because r is 1/2, it's less than 1, I can do this. So I get 5 over 1 minus 1/2. So 5 divided by 1/2, which is 5 times 2 over 1. You'll have lots of practice dividing by fractions, which means you multiply by the reciprocal. So my answer is 10. Go ahead and try this problem. See how you do on that. So once again, pause the video. When you're ready to go on, push play. Okay, writing a repeating decimal as a fraction. Now there's a couple different ways you can do this, and your textbook shows you both ways. One of them is using the infinite geometric series formula. However, I don't think that's the best way to do this, so I'm going to show you another way. Remember that 0.25 repeating means this. So the 0.25 keeps repeating. So I wrote out a few repeats of that. So if we're going to think of this as n, we're going to call that n. Well, then if I were to calculate 100 times n, think about what happens to the decimal point when you multiply by 100. You move it 2 places to the right. So I'm going to have 25.252525 repeating, because the 2 5s are going to keep repeating. Now what I'm going to do is I'm going to subtract both of these. So 100n minus n is 99n. And 25.25 repeating minus 0.25 repeating, all the decimal parts are going to cancel out and be 0, so I'm just left with 25. Now I just divide both sides by 99, and I get 25 over 99. And that's actually all you have to do, which my favorite problem to do is let's change 0.9 repeating. So this is a separate example. So say that n equals 0.9 repeating. Then now on this problem, I only have to go, let me change this a little bit. only the 9 is repeating. So I only have to move the decimal point one place. So I'm going to multiply by 10. So 10 times n is 9.9 repeating. So now I subtract this. 10n minus n is 9n. And when I subtract these, the decimal parts go away, so it's 0, so I just get 9. So n equals 1. But wait a minute. We started off by saying n was 0.9 repeating, and we ended up with saying n equals 1. And this is actually a proof that 0.9 repeating equals 1. And that's true. Go ahead and try this one. Notice the 0.37 is repeating, so you're going to have to move it 2 decimal places. So you're going to go ahead and do this, and when you are ready to go on, then actually that is the end of our lesson. So you have a homework assignment that is up on the board, so please work on that.